This is a short video to help you understand the process of annihilation. It is this process that is used in PET scans in medical imaging. In the last PowerPoint presentation, we saw that fluorine-18, the radioactive isotope, is a positron emitter, so it releases a positive electron. In other words, the antimatter equivalent of the electron. Well, very soon a positron that is emitted will collide with an electron. After all, the positrons are being emitted inside a human body. The human body is full of atoms, and atoms have a lot of electrons in them. So this collision happens very fast and very quickly after the emission of the positron. When these two particles collide, they annihilate. In other words, they totally disappear, and all their mass turns into energy. The energy is seen as photons of gamma radiation. In my brilliant drawing here, you can see that the positron and the electron approach each other and collide in the kind of weird explosion thing happening there in the middle. And as a result, two gamma rays are produced. And the two gamma rays are always in opposite directions. This is due to the conservation of momentum. And both gamma rays are detected by the gamma camera that is used in the PET scan. As a result, the actual position of the annihilation event can be accurately pinpointed by the gamma camera that surrounds the patient. After all, this is the point of the tracer. The point is to find out where did the radioactive fluorine-18 end up, in what cells in the brain. For example, if you had a stroke victim, you might be interested to know what parts of the brain were still functioning or not functioning. So by learning where the positron emitting isotope had ended up, you would be able to gain a three-dimensional map of the damage to the brain of a person following a stroke. Now we see that Einstein comes to our rescue again with his equation E = mc squared that equates the energy and the mass interchange. So for this process, for the positron-electron annihilation event, the mass that has been destroyed or annihilated is equal to the mass of an electron plus another mass of an electron. Because after all, a positron has the same mass as an electron, it just has a different charge. So therefore the mass is 2 times the mass of an electron, as given on the datasheet, coming in at 1.82 times 10 to the minus 30 kilograms. So we can now substitute the mass lost into E = mc squared, and here we are doing it, giving us that the total energy released during the annihilation event is 1.64 times 10 to the minus 13 joules. Now if you remember from the earlier diagram of the annihilation event, there were 2 photons produced, so each photon will only get half of this energy at 8.20 times 10 to the minus 14 joules. And we're going to finish this off by asking the question about the wavelength of the photons. So we can finish off this section by working out the wavelength of the photons that are emitted in this annihilation event using E = hc over lambda. Now I've rearranged it to make lambda the subject to the equation, and I get a wavelength of 2.43 picometers, and with a wavelength in the region of picometers, this is roughly the width of a nucleus, so we're well into the gamma region of the electromagnetic spectrum by the time we get to this number. So there we go, that is a PET scan and the way in which gamma radiation is released by a positron emitting isotope.